The Schrödinger equation describes particles at very small, non-relativistic scales. We solve for the wave function, which relates to the probabilities of finding a particle in some spot. While the Schrödinger equation is very fun and not fun at the same time, there are some problems with it, like how it fails to describe particles traveling at high velocities. To describe particles traveling near the speed of light, like a free electron, we need to switch to a special relativistic equation. To do this, we need to quantize E equals mc squared. To understand what this means, let's use the Schrödinger equation again for a precursor. We know from classical mechanics that the energy of a system is the kinetic energy plus the potential energy. To describe quantum systems, we replace the momentum with the momentum operator, and the energy for the energy operator, also called the Hamiltonian. By making these substitutions, we then obtain this expression. We call this the time-dependent Schrödinger equation. Simple enough, right? In special relativity, we prefer to use a different formula for energy. This reduces to E equals mc squared when the particle has zero momentum. To get a relativistic version of the Schrödinger equation, we need to repeat the same steps. By making the same substitutions, we get this. We then multiply by a field phi, and we have arrived at the Klein-Gordon equation. We have quantized E equals mc squared. This equation is pretty clunky though, so we can switch to natural units where c and h bar equal 1. This may seem like a dubious choice at first, but it actually makes sense. The speed of light and Planck's constant are quantities that depend on units, so we can choose units in which their values are equal to 1. It's like how the velocity of a car can be different when we switch units. To recover our original units, we can just do a hasty unit conversion in the end. Using natural units, we obtain this more simplified equation, and by adopting a new notation, we get this equation over here. By using the Einstein summation convention with the Minkowski metric, we can write this equation even more compactly, like this, and this is a common form of the Klein-Gordon equation. The meaning of the field itself is a bit ambiguous. Is it a wave function? Does it only describe a free particle? What about if the particle is in a potential? All these questions and problems can be answered when we quantize E equals mc squared a second time in what is called second quantization, which we'll be covering soon. So that's how we quantize E equals mc squared. We have already made a solution video to the Klein-Gordon equation, but in our next video, we will be going a step further to derive a more practical version of the solution. Thanks for watching, and until next time.